Good evening and welcome everyone to this long weekend special. We are nearly at the end of our prelim series. We've been preparing these prelim webinars. So we've been covering every topic for the last couple of weeks. And now we're at the last topic phase. The next 2 weeks, we're now doing past paper practice, where we're really just doing revision. So next week is going to be paper 1 revision. We're going to be doing paper 1 maths, paper 1 physical science. The following week is going to be paper 2 revision. At the end of the series, you guys will be so ready to ace your exams. It's not even funny. All right. Before I waste any time, let's jump straight into it. Today, we're doing electrochemistry. Make sure you've got your calculators ready. Make sure you've got pen, you've got paper. Most importantly is a formula sheet. Remember, electrochemistry is about that table of standard reduction potentials. You can't work this section without that table. Make sure you've got your table close by. If you don't have one, it's okay. I'll share one in our presentation as we do go by. But if you do have one, quickly run and grab one. It's going to be very useful. Lastly, if you know you got any friends that either should be in this class right now, or someone you know that will benefit from this session, please make sure you tell that person right now, hey, there's a session on, please join. If you're on TikTok, share the live right now with that person. Make sure that they can come and join. Let's benefit so that everyone can come and nail these upcoming exams. Fantastic. Let me get my whiteboard up and let's get our session going. Give me 2 seconds. Okay, Theo, just confirm if you can see my whiteboard with my summary page.
Yes, I can.
Fantastic, thank you so much. If you are with us for the first time, if you're on TikTok, please note we do these lives Mondays to Thursdays, 6 p.m. to 8 p.m. We appreciate everyone who's joining us for the first time. Welcome. Get ready, get settled. We're going to be here up until 8 p.m. And when you leave here, you're going to be a master at electrochemistry. Very, very important. We've got a goal of reaching 12,000 subscribers and followers on TikTok. We're nearly there. We're at 11,946. That's what, 54 shy. And I'm pretty sure we'll nail that number today. So the aim for today is to get to 12,000 followers on TikTok. Whether you're watching us on Zoom or on TikTok, please just click that follow button and help us get to our goal of 12,000. Okay, without wasting time, let me jump straight into today's content. Remember, it is an interactive session. At any given time, you're welcome to ask questions. You're welcome to engage and interact. How do you ask questions? You basically just post them in the chat. It's that easy. And then at times I'll be asking you questions and I want answers from you. And then how I do that is I'll basically ask you, please post the particular answer in the chat. Sometimes it's a multiple choice question I'll put up. All you have to do is post A, B, C, or D. Other times it'll be an open question, and then simply say increase or decrease or whatever else it is. And let's really all get involved. Let's get engaged in today's session. Okay, I'm going to just switch my video off for the guys on Zoom just to help you save a little bit of data, but then I'll put it back on at the end of the session. Because for now, you don't want to see my ugly face. What you want to see is the content that's going to help you ace your exams that's coming up. All right, electrochemical reactions, right? So electrochemical reactions, we're starting at a base of having to understand what are called redox reactions. Before I get too far, let me just get an indication of who has completed this topic at school or is still busy with it or has not done it at all, right? So please just post in the chat, done with the topic, still busy, or haven't started, just so I have an idea of how to pace the lesson that I'm about to give you guys today. Okay, post in the chat right now. Have you done electrochemistry? Are you still doing it, or you haven't started the topic? Okay. Thanks, Poloso. Thanks, Tlakonolo there for your answer. Anyone on TikTok as well, you're more than welcome to join. Tell me whether you are done with the topic, haven't started, or are still busy with it at school. It helps me know the pacing of how I should kind of go with this topic. Okay, some people are done, some people haven't started, some people are not done. Okay, Leafly on TikTok, thank you so much. You're done with the topic. Great, really appreciate it. Okay. So I'm going to try my best to not be too fast. If I am too fast, please stop me. But remember, these lessons are prepared as a revision lesson. So if you haven't done the topic at school, it might feel like I'm going a little bit too fast. Do not panic. So then what I want you to do, take this as a preview to the topic, so that when you get to school and the topic is done at school, you'll then be able to have a better understanding. Then Remember, go back and do revision on the topic, because every lesson we have here will be recorded. You can go back, watch the recording. We're going to post it on YouTube. Go to the YouTube recording of this topic, and then you can always watch it after the fact if you've done it at school. Those that have done it are still busy. Awesome. You're going to have a good time. Hopefully, it'll make a lot more sense after today when we're dealing with this topic. All right, jumping straight in. So dealing with electrochemical reactions, right? In this case, we're starting off with what we refer to as redox reactions, right? So redox reactions, redox is short for reduction and oxidation, right? So that's the RED is for reduction and the OX is for oxidation. So these are called redox reactions. You should have done these in earlier grades, probably grade 11, where you touched on redox reactions. But as a reminder, redox reactions are reactions in which electrons are transferred. Very, very important. So you're going to have one species donating or losing an electron, one species gaining or accepting an electron, right? So oxidation is what we call the process by which someone loses or species loses an electron. That's called oxidation, right? So your oxidation number will increase in that case, right? And when you get oxidized, we call you the reducing agent. I'll come back to that one just shortly. Then the other side of redox, we're looking at reduction. So reduction, looking here, is the gain of electrons, right? Your oxidation number will decrease when you undergo reduction. And reduction is known as the oxidizing agent. Now, I want to highlight these two terms. I'll keep one in orange. Oxidation is the loss of electrons. Sorry, let me just make my highlighter a lot smaller. So oxidation is the loss of electrons. And we call the substance that undergoes oxidation, we call that the reducing agent, right? And then reduction is a loss of electrons. We do that one in blue. So reduction is a gain of electrons, and we call that the oxidizing agent. Okay, let's quickly unpack this sentence for a bit, especially for those that haven't started the topic. So think of oxidation and reduction as a pair. Those two things have to happen together, right? Usually they happen together. One thing will get reduced and another thing will get oxidized. They're very, very important. So think of it like, I'm going to give you an example of money and exchanging money. So when we exchange money, so let's say I were to ask you to give me money that I will give you back at a later stage. What do we call that? When I ask you to give me money that I'm going to give you back at a later stage, what is that process called? Quickly post in the chat. What is it called when I ask you for money that I'll plan to give you back at a later stage? Quickly post in the chat. What is that? If you ask anyone for money that you plan to give back, what is that process called? I'll give you guys 30 more seconds, 10 seconds to finish typing. What is that process called? If you have no one's answering, you can jump in there and help them with this one. I think we're having a bit of a slower Thursday today with the long weekend amongst us, right? So remember, if I ask you for money that I plan to give back, we call that borrowing, right? And then basically what you did in that case is it's called you are lending me money. So yes, from my perspective, I'm borrowing. From your perspective, you are lending. So the one that gives the money is the lender. The one that takes the money is the borrower. So think about now redox reactions. The one that gives the electron or loses the electron is the reducing agent, or the one that undergoes oxidation. The one that gains or receives the electron is the one that undergoes reduction, or the oxidizing agent. So here's where the agent part comes in. For me to be able to get oxidized, for me to be able to lose an electron, someone has got to be willing to come and receive that electron on the other end, right? So when that process happens, so in me getting oxidized and you getting reduced, you were my oxidizing agent because you helped me undergo oxidation. And when I got oxidized and you got reduced, I am your reducing agent, right? Because I helped you undergo reduction. So anything that undergoes oxidation is going to be a reducing agent, because oxidation means you're helping another species get reduced. Anything that undergoes reduction is the oxidizing agent because it helps the other one get oxidized. I hope that makes sense to you guys. Let's quickly then take our next step and look at in a bit more detail what these look like in chemical reactions, right? So next up, if you look further down, we're going to be looking at this reaction over here. So this is the reaction that we're looking at there, where we've got zinc and copper sulfate becoming zinc sulfate and copper metal. So in that particular case there, we see that zinc is oxidized, right, to form zinc 2 plus. And then what does that look like? So when zinc is oxidized to form zinc 2 plus, we can see this is what we call the half reaction for those that haven't done this topic. The half reaction is basically the 1/2 of our redox. So the big reaction up at the top, this is our redox reaction. And then we can break our redox reaction into half reactions, the oxidation half reaction and the reduction half reaction. The oxidation half reaction is where zinc became zinc 2 plus the 2 electrons that it's lost. On the right-hand side, we can then have a look at what we call our reduction half reaction, where copper ions are reduced into copper metal. So that Cu2 plus gains 2 electrons and becomes copper. When you write in your half reactions, you always write the electrons with a plus in front. So it's never like on the left-hand side. You don't write zinc minus 2 electrons becomes zinc 2 plus. You write it as zinc becomes zinc 2 plus and 2 electrons. Then on the right-hand side, you have copper 2 plus 2 electrons becomes copper, right? Very important. We can see that zinc was oxidized. Therefore, zinc is our reducing agent because it helped copper ions get reduced on the right-hand side. And then copper got reduced, which means our copper ions were the oxidizing agent. They helped zinc get oxidized. I want you to keep remembering those two terms so we can use them interchangeably like that, right? Fantastic. Okay, so let's quickly look at now what we refer to as spontaneous versus non-spontaneous reactions, right? Now, with spontaneous and non-spontaneous reactions, a spontaneous reaction is one that takes place without any external input, meaning I don't have to come and do anything. I don't have to come and add energy. I don't have to do anything. Put the two things together and the reaction will happen without anyone taking part. A redox reaction is spontaneous when the stronger reducing agent undergoes oxidation. This can be defined from the perspective of the strength of oxidizing agents as well. The stronger oxidizing agent undergoes reduction. That'll make a little bit more sense when I introduce the table of standard reduction potentials. Then we can see how do we measure which is the strong reducing agent, which is the strong oxidizing agent, and then how do we then determine, is it spontaneous, is it not spontaneous? We'll look at the table. But what I want you to understand right now is when your stronger reducing agent undergoes oxidation, then you know you're dealing with a spontaneous reaction. And when your stronger oxidizing agent undergoes reduction, then you know you're dealing with a spontaneous reaction. Spontaneous reactions are basically what we're going to use as the basis of what we call a galvanic cell. I'll get to those just now, right? Then a non-spontaneous reaction requires energy from the environment to take place. A redox reaction is non-spontaneous when the stronger reducing agent undergoes reduction, i.e. when the stronger oxidizing agent undergoes oxidation, right? So when the one that really wants to undergo oxidation undergoes reduction instead, or the one that really wants to go through reduction goes through oxidation instead. So it's a bit of an unnatural process for each of those things, which means it usually will then require energy for me to make something happen that wasn't naturally going to happen spontaneously all by itself. Thank you for all of those that are following us on TikTok. I appreciate it. You guys are really helping us hit that goal. Remember, if you've just joined, we've got a goal to hit 12,000 followers by the end of this live. I really appreciate it. We're getting closer. We've got 49 more followers to go. I know you guys can definitely do it. Okay, if you just joined, we're doing electrochemistry. And we're still starting with our summary for the topic for now. After we're done the summary, we're going to go into a past paper question. While you guys join, all the new guys there, please post in the chat whether or not you have done the topic at school. So I want you to post one of three things. You must post done if you've finished the topic at school. Post not done if you're still busy, or haven't started if you have not touched the topic at all. It just helps me know what pace to follow. But thank you guys for joining us. And please remember to share the live with your friends so that they can also benefit. You don't want to pass by yourself. We must all make sure everyone gets to pass. Thanks, Liki. I see that you are done. I appreciate your input there. Yolanda, not done. Thank you. I appreciate your input there. Okay, fantastic. Reese says, done. Please do acids and bases. Reese, stick around for this session because we're going to cover this topic, but acids and bases is done. So if you go to our YouTube page, you'll watch the recording of acids and bases, and then you can catch that one up there. But we're still going to cover it again when we do our revision. So next week, we're starting revision, where we're doing paper 1 revision. So we're doing paper 1 maths and physics revision next week. The week after that, we're doing paper 2 revision, paper 2 maths and chemistry revision. So definitely make sure you stick around for that. It's going to be really, really awesome. And thank you for those that are following us right now as we speak. Appreciate it, guys. Okay. Reese, next week, what time? Mondays to Thursdays, we do our lives from 6 p.m. right up until 8 p.m. Okay, let's jump straight in, guys. Okay, so as mentioned, galvanic cells are based on spontaneous redox reactions, right? And electrolytic cells are based on non-spontaneous redox reactions. So let's go back and look at what was this thing. I kept talking about stronger reducing agents and stronger oxidizing agents. What does that mean? And how do we tell when one is a stronger reducing or stronger oxidizing? So we use the table that we call the table of standard reduction potentials, right? Now, a little bit of history about this table. What you guys will see when you look at the table. Let me quickly go. I've got the table in my notes somewhere here. Let me quickly go down to my formula sheet. All right, you'll see this table here, right? I know a lot of you guys use table 4B. I'll show you today. 4B or 4A doesn't really matter. I'll show you how to really understand and work with the table during today's lesson. So if you want to make sure you catch that, stick around till the very end, right? So this is the table of standard reduction potentials, which what you can see on one side. So you can see there, it'll tell you on the right-hand side, increasing strength of, let me quickly make my highlights a little bit bigger. So increasing strength of reducing agents on this side here as we go up, right? So as we go up, I have stronger reducing agents. And then as we go down on the other side, I've got stronger oxidizing agents, right? What does that roughly mean? It means as I go further up on my right-hand side, I will find strong reducing agents, substances that are more willing to spontaneously undergo oxidation. On the left-hand side, it says I've got increasing strength of oxidizing agents as I go down. So on the left-hand side, as I go down, I'm going to have substances that more readily want to spontaneously undergo reduction, right? So when I say on the left-hand side and right-hand side, what I'm talking about is like this. So when I say, for example, platinum over here, that is the substance that as I go down, we have increasing strength of oxidizing agents or oxidizing ability. They really want to undergo reduction on the left-hand side. And then as I go up on the right-hand side, I'm looking at substances like, for example, copper. Copper is going to be a much stronger reducing agent than whatever comes underneath it, like that water, like the other copper 1, like iron 2, anything like that, right? So the more I go up on the right-hand side, the more I find strong reducing agents, substances that are willing to or have a likelihood of spontaneously undergoing oxidation. As I go down on the left-hand side, I have things that have increasing strength with their oxidizing ability. So they're more likely to undergo reduction spontaneously. So let's quickly go back to our notes and you can have a quick look at that as well. So in our notes, it breaks down that table. So when you look at that table there, again, same kind of story. When I read my table, it's very important. So when I read my table from left to right, left to right, I am looking at a reduction reaction. Let me quickly make that a little bit smaller so it's more manageable to look at. So from left to right, I'm undergoing reduction. So you see there, manganese 2 plus 2 electrons gives me manganese metal. So you can see there, manganese 2 plus gained 2 electrons to become manganese metal. That's a reduction half reaction. Remember, these are half reactions. But if I read it from the right to the left, then I'm looking at oxidation, right? From right to left, I'm looking at oxidation. What does that mean? So it means iron goes to the left like that. Oxidation is lost. So iron becomes iron 2 plus 2 electrons. So that's a little example of reading it from right to left is reduction. Reading it from left to right is reduction. Reading from right to left is oxidation. Very, very important. And then I mentioned already something that's very important there, that increasing reducing ability, right? So when I say increasing reducing ability, that's sort of going up like this, means things further up are going to be more likely to undergo oxidation. But if I've got increasing oxidizing ability, it means things further down are going to be more likely to undergo reduction, right? Very, very important. That's how we read it. And then what I also say at the end of the day is look at your E naught values, right? The more positive your E naught value, right? Not that only the positive ones, but my words are quite clear. The more positive my E naught value, the more likely that substance is going to undergo reduction. The more negative my E naught value, the more likely it's going to undergo oxidation, right? So example, with reference to the relative strengths of the oxidizing agents, explain whether the reaction between manganese and iron, iron ions, Fe2+, is spontaneous or non-spontaneous. So we go first of all and find our two species, right? So I'm going to find my first species. Let me go find my iron 2+. So that's my iron ion in that case there. And then I'm going to find my second species, which is my manganese metal, my full-on manganese, not the ion, right? Then we have a look at what happens in that case there. So we can see that Fe2+ is a stronger oxidizing agent, right, than manganese, since it is lower on the table, or it's got a more positive E naught value, right? Which means Fe2+ is going to undergo reduction to form Fe. So we can clearly see that on that side there. Therefore, the stronger oxidizing agent undergoes reduction, as we expect, which means the reaction between Fe2+ and manganese will be spontaneous. You can also look at this from the other side. The other side being, I'm going to look at manganese up at the top, and I can say, okay, here's my manganese over there. Manganese has a greater reducing ability than iron 2+, right? So when manganese has got a stronger reducing ability, it means it's going to be more likely to undergo oxidation because it's going to help something else get reduced. So because it's more likely to undergo oxidation, we can clearly see it's on the right-hand side, it's going to go in this direction of my reaction. It will get oxidized because manganese will lose 2 electrons to become manganese 2+. Therefore, the stronger reducing agent underwent oxidation. This is going to be a spontaneous reaction. I want you guys to really make sure you understand this. So especially those that have done the topic or are doing the topic, I hope this makes a lot more sense at this point. And then for those that haven't done the topic, if it's still feeling a little bit tricky, don't panic, don't stress. You will get it to do it at school. And when you hear it for the second time, it'll make a lot more sense. Don't forget to come back and watch this lesson again. Go watch the recording of this lesson so that you can solidify that knowledge and you know how to apply it. Prelims are about to start very, very soon. And I want you guys to be able to knock out every single topic that we're going to be dealing with. Fantastic. Okay. So again, remember guys, if you're not following me 100%, don't panic. Do not panic right now, because we're going to go through questions where we get to apply this thing. And usually when we apply, things tend to make a lot more sense. Okay. I've got some questions I need to quickly answer right now. Let me just pause for some questions. If you've got questions at this point, please post them in the chat and I will quickly go through them. So Poloso asks, how does manganese lose the electrons? So again, what you can see in this case here, so when you look at manganese over there, right? So in this reaction, manganese can basically only go one direction. It can go to the left, right? You can't really, there's no reaction this way. The reaction is going to be that way, which means my manganese has excess, has an electron that it can lose. And in this case, it's 2 electrons. So when we look at that, it's going to then lose those 2 electrons. When you have to think about exactly how, I don't know, maybe if I understand your question fully, Poloso, but you know, when you look at all our electrons, so all our, not electrons, but our atoms, they have the ability to either gain or lose a certain number of electrons. So remember when we were looking essentially at, I think in like grade 8 and 9 and 10, when you're learning about the periodic table, grade 9 and 10 more specifically is mainly grade 10. When you learn about the periodic table and the various periods and, you know, your valencies, +1, +2, up to ±4, -3, -2, -1, which really then you look at certain atoms have the ability to kind of, when they want to have a full outer energy, not energy thing, but outer electron shell, they will either gain or lose a certain number of electrons. And then when you look at something like manganese, it's going to have a valency of +2, meaning if manganese were to lose electrons, it's going to lose 2 electrons. It's in its nature, right? That's why the table is there to help you figure out how many. You don't have to worry about how many it's going to lose in a particular case. The table is there to work it out. Sometimes what you will see on the table, you'll see more than one, right? You'll see more than one version. So like something like copper, you've got copper 1 and you've got copper 2, where copper can either lose 1 or copper can lose 2, right? You can see even on this very table, you've got chromium losing 2 or chromium losing 3. At the end of the day, for me, find the strongest reducing agent or find the strongest oxidizing agent, and that will basically tell you which one you pick of the two. I hope that answers your question, Poloso, a little bit. Let me see, we've got questions there on TikTok. Osiro says, I always miss the starting of the videos. Osiro, remember, start at 6 p.m. straight. If you missed, don't worry, we are not far into the lesson. You have an hour and a half left. You'll still gain a lot of knowledge from the session here. So, and if you want to go back and watch the beginning of the lesson, remember just to go back to our YouTube. We post the recordings there and you can catch the recording there, right? On YouTube, just look for the Learning Space ZA, or even just go youtube.com/the Learning Space ZA. Then you guys will do well in that case there. Sero says same. Don't stress, guys. We're going to still do a lot of work today. You guys are covered. Okay. Then, Kante, which copper do we use? Because I think they are 3. So I think, Mulalo, I hope I answered your question when I was answering Poloso's question, right? You'll see, hopefully one of the questions we'll have an example where they'll say copper, but then there's copper 2, there's copper 1, or whatever else. And then in that case, just look for the strongest reducing agent or the strongest oxidizing agent. Sometimes it'll be copper 1 or it'll be copper 2. I'll show you how you do that on the table as we work through the table. Okay. And then I think that was the last question there on TikTok. Thank you for everyone who's been following us. I appreciate it. We're that much closer. We're only 40 people away from reaching our goal of 12,000. So anyone who's joined us right now that hasn't followed us, please follow us. We're trying to get to 12,000 followers on TikTok, and it's all because of you guys. All right. Cool. Let's go to the next part of our question now. And we're going to go look now at electrochemical cells. So initially we've been dealing with the redox reactions and just the reactions generally. So now we need to look at, well, how do we then take these reactions and make them really useful to us, right? So when we do electrochemical cells, I want you to remember these 3 key things: N-ox, red cat, and then electrolyte sometimes becomes very useful as well. So N-ox refers to the anode is the electrode where oxidation happens. That's why it's N-ox. And then red cat, it's a reminder to just to say the reduction happens at the cathode. The cathode is the electrode where reduction takes place. And if you hear the word electrolyte being thrown around, again, electrolyte is a solution or liquid or dissolved substance that basically conducts electricity through the movement of ions. And then we usually use electrolytes in our half cells. So you can see here, we've got a galvanic cell, right? And then when you're dealing with a galvanic cell, galvanic cells convert certain amounts of energy to a certain other kind of energy, right? And then you'll see the same thing with electrolytic cells. So galvanic cells, the energy conversion that takes place there is going to be chemical energy to electrical energy. So what we're doing here is that we're taking a reaction that was spontaneous and we are harnessing electrical energy out of it. So remember, how can we do this? At the beginning of the session, what did I say? I said that redox reactions are reactions where electrons are transferred. That's very important. So when we transfer electrons between 2 atoms or 2 species, right, that electron going from one space to the other is a flow of charge. And a flow of charge is electricity, it's current, right? That's why we can then take this and say, oh, if I take a spontaneous reaction, make one given electron away, one will receive an electron, I can actually make effective work out of that electron. I can harness the energy that that electron possesses and use it for something that else I need. So every battery that you know, right, most of them are going to be some kind of electrochemical cell. Gel batteries, lead acid batteries, even your lithium-based batteries are usually all going to be using the principle of redox reactions, and they're going to be what we call electrochemical cells. So again, let's look at the example of a copper zinc galvanic cell. So in this particular cell, I need us to understand how the cell is built up, right? Remembering the cell is going to be using the principle of redox reactions. Now, we're going to have two half cells. So what I mean by half cells is that this is a half cell and that is a half cell, right? Joined in the middle by what we call our salt bridge. Now, when we look at this, so we're going to have what we call a zinc half cell and a copper half cell. And the half cell, we normally name it based on what the electrode or the main species being oxidized or reduced is going to be in that half cell. So in this case, we're dealing with zinc being oxidized. We're going to call that our zinc half cell. So we have a zinc electrode. The electrode is this piece here. It'll usually be made out of some substance that can conduct electricity. You will find that sometimes you want to reduce or oxidize gases, right? And when you want to reduce or oxidize a gas, you're like, well, gases don't conduct electricity. In that case, you need to then use an electrode that will be inert. What do I mean by inert? One that doesn't readily react. So usually we'll use platinum as our inert metal, and we'll just bubble the gas through that electrode. And that will help us then conduct the electricity without that electrode taking part or really interfering in what we're doing. So on the left-hand side, we're going to have our zinc electrode. So here's our zinc electrode. It's made of zinc metal. Now, zinc is oxidized, right? So that's going to be our anode, because remember we said anox. Anox means the anode is where oxidation happens. Now, what do I mean by oxidation? Remember, going back to our definition, oxidation is the loss of electrons, right? So when that happens, zinc, this is, let me just make my pen a little bit smaller, just so I can write a bit better there. Okay, so when we look at this, this is going to be a zinc electrode. Let me just zoom into this half cell. As it gets oxidized, we're going to basically have this half reaction taking place where zinc becomes zinc 2 plus 2 electrons. So when my zinc gets oxidized, you'll see that I'm going to have zinc 2 plus going into solution. And then I'm going to have the electron, right? Or in this case, the 2 electrons are going to then go up here. They're going to go through my external circuit, through my voltmeter. The voltmeter simply just represents anything that's going to be using my electrical energy. But in this case, we're just measuring the potential with our voltmeter, right? So it'll go through there. We're going to use that electron, whatever. It'll get to the other side. And as the electron lands on the other side, we now know that we are ready to do what? Something is going to gain that electron, right? So I'm going to quickly look at the other side and say, oh, copper on the other side gets reduced. Reduction is the gain of electrons, meaning on the other side, I'm going to have Cu2 plus in solution. That's going to come join with 2 electrons and become copper metal and make my electrode bigger, all right? So we can see in this case there that our cathode is going to be positively charged in the galvanic cell, anode is negatively charged in the galvanic cell. And that's basically the life cycle of what's going to happen, right? So as we see on the left-hand side, I'm going to end up with zinc going into solution, becoming zinc 2 plus. The 2 electrons from zinc are going to go up through my voltmeter, come down. Copper 2 plus is going to pick up those electrons and become copper metal. So that's the key thing that happens here. That's the life cycle of this. But one thing is going to start happening as this happens, right? So we did chemical equilibrium a few sessions ago. Now, as this thing happens more and more and more, you should start noticing a little bit of a problem. The right-hand side is going to become more and more positive, right? It's going to become more and more positive because every time I keep adding zinc 2 plus, zinc 2 plus, zinc 2 plus, zinc 2 plus, I'm adding a lot of positive ions on the left-hand side. And at the same time, my left-hand side becomes more and more negative, right? In terms of my electrolyte. Don't think about the electrode, but the electrolyte. Because I'm removing copper 2 plus, I'm leaving sulfate ion, so SO2 minus. I'm removing copper 2 plus, I'm leaving SO4 2 minus. So I have more and more negative ions on my right-hand side, right? And now I'm going to have a little bit of a chemical and electrical imbalance. How do we solve that? That's where this wonder thing comes in, right? We call this our salt bridge. The salt bridge has got a number of functions that we'll go through right now. But the first thing I want you guys to see is what our salt bridge will do. It's going to deposit ions to help maintain electrical neutrality in our solution, because my left-hand side gets more and more positive, my right-hand side gets more and more negative. The salt bridge is going to save me by depositing ions. So what's going to happen is my salt bridge is going to then go, it's going to have silver nitrate in solution. So you're going to have Ag plus and NO3 minus. And then Ag plus is going to go on the side that becomes negative to make it more positive. So it'll deposit here. Let me quickly just make this smaller. So I'm going to deposit Ag plus from my salt bridge to counteract the negativity of what's remaining. And on the right-hand side, my salt bridge is going to deposit my NO3 minus, just to help add negativity to the positive side of my salt bridge. And that's called maintaining electrical neutrality, because I want my half cells to be as neutral as possible. The more they go away from being neutral, I slow down my cell, which means my voltage is going to get reduced in my cell, right? And that's not really what I want at the end of the day. Okay, so let's quickly look at what happens in each of the half cells now. So in the zinc half cell, we said this is the half reaction that takes place in our zinc half cell. We've got zinc being oxidized into zinc 2 plus, and then the 2 electrons go over to the other side. And then the mass of the zinc electrode will decrease because I had zinc metal and zinc 2 plus goes out. Zinc 2 plus goes out, the electron goes out. So it's going to get smaller and smaller and smaller, right? The concentration of zinc 2 plus ions will increase, like I showed you guys there, right? As I keep depositing this zinc 2 plus, I'm going to increase the concentration of zinc 2 plus, and then an excess positive charge in the half cell is going to develop, right? So what ends up happening there is that negative ions now, my NO3 minus is going to flow through the salt bridge into my half cell in that case there. So what can also happen is the SO4 minus from the other side can also go all the way through my salt bridge down into my zinc half cell. Then let's look at what happens in our copper half cell. So in our copper half cell, what happens is that we see copper gets reduced. So copper 2 plus in solution gets the 2 electrons from the zinc that went all the way around and becomes copper metal. Let me just write the 2 electrons there, just so if people are joining mid-session, they don't get confused about what is happening. So there's 2 electrons essentially that go from one side to the other side, but it's not 2. It's going to be a lot of electrons flowing. Just that each copper 2 plus will only pick up 2 as it happens, right? So the mass of our copper electrode is going to increase because I'm reducing copper onto my electrode. The concentration of Cu2 plus ions will decrease because I'm taking them out of my solution, meaning I'm going to have a surplus of SO4 2 minus ions left in the half cell. That half cell becomes more and more negative, like I said to you guys. And then what ends up happening there is I'm going to have silver ions being deposited down, and sometimes also my Zn, my zinc 2 plus ions from the one side will go through my salt bridge and come around and land into the copper half cell. And that's the key thing, is that it wants to maintain that electrical neutrality. Very, very important, right? So the thing I said now, we need to look at more detail into the salt bridge, right? Is then what are the uses of the salt bridge? So the salt bridge has 3 key uses. I've gone through one of them with you guys there, which is the last one. It keeps the, second one, it maintains electrical neutrality in each of the half cells, because that helps me ensure that I've got the best voltage, the best potential difference for my cell. If I lose that electrical neutrality, my potential difference goes down and down and down. That's when you basically have your battery flat or your battery running out, because I've reached an equilibrium point in my battery. So, but the first big reason is that what's the function of a salt bridge? The salt bridge completes the circuit. Very, very important. Salt bridge completes the circuit. And then salt bridge also does what? It maintains electrical neutrality in each of the half cells. And then finally, it keeps the electrolytes separate, right? And that's one of the most important things, because sometimes you don't want that reaction to happen in the containers. You want it to happen through the external circuit, because the external circuit is where I want my electrons to flow, so I can use them in this particular case. All right, then again, The salt bridge must have positive and negative ions in solution in order to function. That's why we normally use, it's called a salt bridge. So salt bridge doesn't mean NaCl, doesn't mean table salt. It means an ionic compound in aqueous solution. That's the salt bridge, right? Something that's an ionic compound is going to have a positive ion and a negative ion coming together to mix up there. Very important. Care must be taken to choose a salt that will not form a precipitate when when reacting with any of the electrolytes. So this is something you guys should have done in grade 10, right? Reactions of aqueous solutions where certain things are not soluble and they form precipitate. So very important, you need to know and keep a lookout on that. If it happens during one of our questions, I'll make a note and I'll show you guys. And then B, also something we need to keep out for is that the substance in my salt bridge should not undergo oxidation or reduction instead of the chemical species selected for the cell. What do I mean by that? So remembering the fact that I've got nitrate ions that are being deposited on the left side, I've got silver ions deposited on the right-hand side. I need to make sure that when the silver goes in, it doesn't take over the reduction that copper is doing there. Also, on the left-hand side, I need to make sure that my nitrate doesn't take over the oxidation that zinc is doing on the left-hand side there, because that's very important. Because if that happens, I lose the efficacy of my entire thing. My battery becomes useless, it stops working, and then it's no longer an electrochemical cell. It becomes something that just happens and doesn't really give any useful work to anyone. So that's quite important. Okay. And then let's touch on cell notation, and then finally we'll quickly go on electrolytic cells. I know there's a lot of information that's coming through, guys, but I really want to make sure that you guys catch it well, because some of you have not done this topic at school. So I need to give you as much information as possible. And then I'll make sure that by 7 o'clock, I'm done with the theory. And then we're going to practical stuff from 7 o'clock up until 8 o'clock. And we're going to have lots of time to practice a full galvanic cell question and then also a full electrolytic cell question. So don't stress, don't panic. If there are any questions as I'm busy with this, please post them in the chat. It's very, very useful. If anyone has just joined us on TikTok, thank you and welcome for joining us. I appreciate everyone that's been following us. We are at we're very close. We're very close. We're at 11968. Our goal is to hit 12,000 followers for the day. We're really, really close. We're 32 followers away. I know you guys can do it. So please make sure you guys follow us on TikTok as well. If you just joined us and you missed the first half of the lesson, don't panic, don't leave, stick around, right? You'll still benefit from the question section. And also, we're going to have a recording that you can go watch on our YouTube channel. To find our YouTube channel, go to youtube.com/thelearningspaceZA, or just go to our TikTok page and then we'll have a link to our YouTube page right there. Okay, let's jump into cell notation. Cell notation, again, is what we use to represent galvanic cells, right? Electrodes are written on the outside of the cell notation. Phases of substances and their concentrations or pressures can be included in the cell notation. Please note, it's not a reaction. Therefore, no balancing of numbers is required. The anode is placed on the left-hand side and the cathode is placed on the right-hand side. Then the first thing you need to look at, what are our active electrodes? So we can see there the same cell we're dealing with here. It was a zinc and copper cell. So then we know on the left-hand side, we're going to have our zinc there. On the right-hand side, we're going to have our copper there. And then basically what it shows you is how this whole process happens. So zinc becomes zinc 2+ on the left-hand side. Very important, you need to put this double line in the middle. This double line represents your salt bridge, all right? So you have zinc solid becomes zinc 2+ aqueous solution. So it was the reducing agent and then the oxidized species. Then on the right-hand side there, we see the oxidizing agent in the reduced species. So oxidizing agent was our Cu2+, and that became Cu solid. And then that's how you write your cell notation. And then what happens if we were dealing with maybe a gas, right? And in this case here, so remember what I mentioned before, is when we're dealing with gases, gases don't conduct electricity by themselves. We need to include an inert electrode. So in this case is our example of our inert electrodes, and there you can see platinum is the inert electrode. So you write platinum slash, then you can see my Cl there. And on the other side there, I've got my platinum to show that even fluorine on the other side was in the presence of platinum. Platinum conducted the electricity for me in that case there. So it's quite important. They'll usually give you a question of cell notation or net balanced chemical reaction, etc. Okay. I'm nearly done, guys. We're quickly going to look at how we then combine our half cells. That's now what I was referring to as your net ionic reaction in that case there. So when we combine our half reactions, you need to, number one, identify the half reactions from the table of standard reduction potentials, right? Write them as they are in that case there. Number two, write the two reactions underneath each other. So you can see I had my one half reaction here, my silver becoming silver ion. The other reaction was my zinc getting reduced into zinc metal. All right, those are my two reactions there. And with those two reactions, I need to then write them one underneath the other. What I find very useful is to put my arrows all in the same place. And then what I do, the next step is make sure you balance your number of electrons, because you'll see silver only has one electron, zinc has two electrons. So I need to balance my electrons. So then basically I'll multiply this whole line by 2 so that I can balance my number of electrons. So that at the end of the day, when I'm looking back at this, I've got 2 electrons here and 2 electrons there. That's why it's important to multiply the 1 by 2. Sometimes you'll have a case where one is 2 electrons and one is 3 electrons, right? And in that case there, what you need to do is then multiply the 1 by 2, multiply the 1 by 3, so that you've got 6 electrons in total. And that really becomes how you will work through that. Now, again, combine the reactants on one side and the products on the other side and leave out my electrons. So what you'll see is in that case, I will then, my zinc will go down and remain exactly as it is. My silver will go down, remain exactly as it is. I will leave out the electron. And then on the other side, my silver ion and my zinc as well will come down. So then this becomes my final ionic reaction at the very end, and zinc 2 plus 2 Ag becomes zinc and 2 Ag plus. We'll see how we implement this thing as we do go. Satla's got a question. This is a great time for me to pause. Satla, if you're not typing your question down, let me quickly let you unmute. If it's an academic question, then we can quickly go through it together. I'm going to ask you to unmute, and then you can quickly give us what your question is. Yes, how are you?
I want to know that how do we write the cell notation? Are we starting with the, let me see. Are we starting with the cathode or anode?
Okay, so let's quickly go back down to our cell notation, right? So again, you can see there, the anode is placed on the left and the cathode is placed on the right. There we go. So it says anode on the left. So you see my reducing agent is what goes through oxidation. Oxidation happens at the anode and ox. So oxidation and then reduction afterwards. I hope that answers your question, Cecil. Okay, hope you're covered. Thank you so much. Let me quickly come back and wrap up. 7 minutes to finish the theory part. And then just want to check if there's no questions on the TikTok side as well. No, we are all covered. Okay, if you guys are happy for me to move on, you guys know how I like it done. Give me a thumbs up in the chat. Just put a thumbs up emoji in the chat, then I know that it means you guys are still with me. You're happy for me to go on. Let's take that quick pause. If you're not with me, please post your question now. Thanks on Zoom. I'm seeing all the thumbs up there. Maybe on TikTok as well. If you guys are with me, post a thumbs up emoji in the chat, and I know you're with me. Nokubonga, thank you so much. Cass, thank you so much. Okay. Prime, thank you so much. Okay, you guys are with me. I can move straight on. Then we're looking at standard conditions and calculating the EMF of my cell, right? So how I need to look at this, very, very important. Standard conditions, we need to look at the temperature of 25 degrees Celsius, the concentration of 1 mole per decimeter cubed, and a pressure of 1 atmosphere. Those are the my standard cell conditions. If I can just quickly highlight them and put them there, right? The EMF can only be calculated using the table of standard reduction potentials if the cell is at standard conditions, because these E0 values, right, were basically developed at standard conditions. So really appreciate making sure that we utilize that very, very, very much. Okay. Then also, now a positive value for EMF under standard conditions indicates a spontaneous redox reaction. And a negative value will indicate a non-spontaneous one. The negative value basically tells you how much potential difference or energy you've got to put in to make that reaction happen. A positive E cell value says this is how much energy or potential difference you will get out should you put this reaction together. That's a very important thing. So remember, galvanic cells do what? We take chemical energy and create electrical energy. That's a galvanic cell. So you'll usually get a positive E cell value. Electrolytic cells is now taking electrical energy and creating chemical energy. You'll see how we do that just now. And that will usually give you a negative E cell value. And it tells you how much energy you must supply or what voltage to supply for this particular reaction to take place. Now, finally, let's have a look at our electrolytic cells. So again, electrolytic cells now have an energy conversion that looks as follows. Oh, before I forget, sorry, the E cell calculation is going to be the E value of cathode minus anode, right? So E cathode minus E anode will give you the E cell value. We'll do that. It'll probably ask us somewhere down there, and we'll do that all together. So electrolytic cells. Now, when dealing with electrolytic cells there, the energy conversion is electrical energy to chemical energy, right? So then we've got what we call electrolysis. Electrolysis is the use of electrical energy to produce a chemical change, right? It only works with direct current, right? Power source, as electrons must constantly flow in the same direction. We did motors and generators the other day, and you saw we were dealing with alternating current. And the problem with alternating current, electrons are going to go one way and then they're going to come the other way. So we're not going to actually do anything. We're going to reduce and then undo that in like the next second. So it doesn't really help us. So we need a DC power source. And again, these are based on non-spontaneous reactions. So usually with electrolytic cells, we're trying to make something happen that wasn't traditionally going to happen. So let's have a look. So you can see now with electrolytic cells, I'll give the example of the decomposition of copper chloride. The difference you can see now is usually in electrolytic cells, we don't have two half cells. It's usually just one big cell, but still we have two electrodes, right? So with the two electrodes there, a DC power source, we're going to have, in this case, graphite electrodes, because the stuff we're wanting to work on is going to already be in solution. So we use graphite electrodes. My anode is positive and my cathode is negative for the electrolytic cell. Very, very important. Then let's see what happens. So we've got CuCl2, which is our copper chloride solution. At the anode, right, what happens is copper chloride gets oxidized into, chloride ions get oxidized into chlorine gas and 2 electrons. So you can see that on the left-hand side there. Chloride ions get oxidized. They lose an electron and become chlorine gas. That's the same gas you see that's going to be bubbling off at that electrode. So you'll see bubbles forming at that electrode there. On the other side, you're going to have copper, right? You're going to have copper 2+ ions in solution, gaining electrons and becoming copper metal. And then this electrode here is soon going to be coated with copper. So you'll see that copper, it'll start changing color and becoming a little bit more orange, like what you see, that little copper color. Not orange, but it's like a, copper, like a little bronzy kind of color. I'm saying orange because that's the color I'm using right now. And then we can see, again, at the anode, that chloride ions flow to the anode, and then the electrons flow from anode to cathode. So the electrons will flow from anode to cathode. So what's going to happen there is our Cl2 minus, let me quickly change my pen color. We're going to have our our 2Cl minus, right, is going to go there. It's going to give off an electron. That electron is going to then flow up this way, that way, that way, and it's going to come on this side. I know right now it looks like I'm drawing the wrong direction, right? But remember, when we do electric circuits, this was developed for conventional current, because they thought, conventional current, old scientists were like, positive is the right thing. So they thought, when we're dealing with current, the positive charge is what flows. That's why they used to have the positive side as the conventional current. But we later learned that actually what carries current for electric circuits is going to be electrons. So electron flow is going to be the opposite direction of conventional current. because conventional current is the old way of how we did it. In this case, it's electron flow. So electron flow is going to go the opposite direction, come down there. When the electrons come down on the side of copper, you will see you will have copper ions in your solution, and your copper ions in your solution, you'll have, sorry, let me choose a slightly smaller pen there. Our copper 2+ is going to go on there, pick up 2 electrons and become copper metal. And that's what we can see right here, right? It's that half reaction that we can see. And then the electrons will flow from cathode to anode, as mentioned already. In this case there, right? So note that copper ions in solution are blue, thus the electrolyte turns from blue to colorless, right? Copper ion concentration decreases. So if you've ever seen copper sulfate is going to be a blue substance, right? Because copper ions are blue, but copper metal is that orange color. So as I have less and less copper ions in my solution, the solution goes less blue and becomes more colorless because I'm removing all of those copper ions in my solution, and they're becoming copper metal. Okay. Now, some of the uses of chemical cells, in particular, your electrolytic cells. So we've got the following there. I'm quickly going to name them. So we've got electroplating as one of the uses there, right? Electroplating is when we want to put a certain metal on the outside of another metal. So let's say you want to make jewelry, you can't afford to, buy gold at its full price, but you'll take maybe like brass or bronze and you want to coat it in gold so that to give it the look of gold without having the expense of gold. You will do what we call electroplating. Right? So again, in electroplating, the anode is oxidized and the metal ions move into solution. The metal ions in solution are reduced and form a solid layer on the cathode. Therefore, ion concentration in liquid remains constant because I'm oxidizing one side and reducing the other side, right? We'll look at a quick example of that. The purpose is to make a coated object look nice or to protect the metal underneath from corrosion or other forms of damage. That's electroplating. Refining of copper. So impure copper anode is oxidized. Copper ions are reduced to form pure copper on the cathode. Impurities form sludge at the bottom of the container. I'll give you 2 examples of electroplating and electrorefining just before we start with the electrolytic cell question. Then you've also got the last 2, electrolysis of brine, where concentrated brine, NaCl, is electrolyzed to produce chlorine and hydrogen gas, as well as sodium hydroxide. These 3 products are used in many important industries, right? And then we finally got the recovery of aluminium from bauxite or, ore containing alumina. Alumina, which is aluminium oxide, is dissolved in cryolite and electrolyzed to form aluminium. 7 minutes past 3, I'm 3 minutes late, but it's okay. We're still okay. I'm going to put up some questions for you guys to try now. So remember, like I mentioned, for those who just joined us, I'm going to put up a multiple choice question. I want you guys to answer the question simply by posting the answer that you think it is, A, B, C, or D, right? So the first question is going to be as follows. 1.9. So 1.9 says, which of the following statements is true for an oxidizing agent? A, it gains electrons. B, it causes other species in the reaction to be reduced. C, its oxidation number does not change during a chemical reaction. D, its oxidation number increases during a chemical reaction. All I want you guys to do on TikTok and on Zoom, just post the answer that you think is the right one. Post A, B, C, or D. I'm going to give you guys 2 minutes for that question. Thanks, Denyuko, for your answer. Thanks, Kitumetsi. Thanks, Shudufato. Thanks, Setla, for you guys' answers. Thanks, Kansani. Okubonga, thank you so much. Thank you, Prime. Thanks, Rossi. Okay, for those that haven't answered, guys, quickly, you've got 15 seconds to go. Remember, it's very, very important. Never, ever leave a question blank, especially multiple choice. Guess, you've got a 25% chance of getting it right. So just post your answer, even if it's a guess. I would really appreciate it. And thank you for everyone that's been following us on TikTok. We've got a goal of reaching 12,000 followers. We are now at 11,980. We're only 20 followers away. So if you're watching our live right now and you're not following us, pause, answer your question first, and then click the follow button. We would really appreciate it. Thank you guys so much. and then share the live so that your friends can come and join us along. If you're watching on Zoom and you've answered your question, pop up to TikTok quickly and follow us. Make sure you're following us on TikTok. Really appreciate it, guys. Okay, 5, 4, post your questions quickly. 3, 2, and 1. Okay, let's have a look at what's happening. I see a lot of A's. There are a couple of B's on TikTok, on Zoom. I see a lot of A's. There's a few B's as well. Let's look at what the correct answer would be, right? So which one of the following statements is true for an oxidizing agent? It gains electrons. It causes other species to be in the reaction to be reduced. Oxidation number does not change, or its oxidation number increases, right? So the correct answer for this question, drum roll please, is going to be A, right? It gains electrons. So remember, when we are dealing in this case with, let me quickly, there we go, highlight it, an oxidizing agent does what? It undergoes reduction. Reduction is the gain of electrons. Very, very important. So if undergoes reductions, why would it not be B? Because it can't cause something else to be reduced. It's an oxidizing agent. It causes something else to be oxidized, right? So it can't be B. Oxidation number does not change. Of course it'll change. It's undergoing an oxidation reaction. And then its oxidation number increases during a chemical reaction. No, it doesn't. If something is reduced, its oxidation number will then decrease in that case there. So let's take that down. If you didn't get it right, don't fret, don't panic. There's another chance to redeem yourself. I'm going to give you guys another question, and let's see how you guys do with this one, right? So we've got 1.10. It's a bit of a longer one. I hope it will fit on the screen. Wait, sorry, 1.10 is just that one there. So 1.10 says, which one of the following metals will reduce, right, CD2 plus to CD, but will not reduce Mn2 plus to Mn? This is where you need your table of reduction potentials. If you don't have one, it's important that you do get one somewhere quickly. So pull out your formula sheets, pull out your textbook, and quickly have a look. So which one of the following metals will reduce CD2 plus to CD, but not reduce Mn2 plus to Mn? Is it zinc? Is it silver? Is it nickel? Or is it, my brain just stopped for Mg, magnesium, right? Quickly post the A, B, C, or D. Which one do you think is the right one? Thank you, Cass, for your answer there, for your speedy response. Thanks, Keith Dumets, as well on your side. Guys, quickly have a look at your table of reduction potentials. And then you guys can try and see which one is going to be the one that's going to be happen there. Seta, thank you so much for your answer. Thanks, Masero, for your answer. Okay. Guys on TikTok, if you've just joined us, there's a question on the screen. Quickly just give us the answer that you think it is. We're going to go through the answer together, but you normally, it really helps if you start by giving your answer, and then I'll show you which is the correct answer and why the other answers might not be correct. Quickly have a look. I'll give you guys 60 more seconds so that you guys can go have a look at your table of reduction potentials. It's a very big hint I'm giving you guys there. Thanks, Masima. Thanks, Danyiko, for your answer. Thanks, Kansani, and thanks, Tuba, as well. Thank you, Prime. Thanks, Tapelo and Rosina. Thanks, Havatloli. Okay, I'll give you 10 more seconds to go. Thanks, Tuki. Thanks, Oseho. Okay. Guys, remember, if you haven't answered, this is the time to just guess, right? You got a 25% chance of getting it right. Please just post in there. Lebohang says, hi, I'm new. Welcome, Lebohang, for joining us today. Please quickly just post an answer to what you guys think the answer is. 5, 4, like I said, if you haven't answered, just guess. 3, 2, and 1. Okay, let's have a look at what the answers that were given. I'll start with the TikTok gang. I've got a lot of A's, and I see there was like 1 C. And then on Zoom, I've got a lot of A's, I've got a lot of A's. I've only got A's on Zoom. Okay, let's look at what the actual answer is. Drum roll, please. The correct answer for this one is going to be, drum roll, drum roll, drum roll, A, zinc, right? And then the question is, well, why, how? Let's quickly go look at our table of reduction potentials, and I'll show you how to figure this particular one. Remember, the question's asking which one of the metals will reduce CD, but not manganese, right? So let's quickly go have a look at our table of reduction potentials. Quickly go down. Let me use table 4B. It's the one that you guys use at school. So I'll use that one, but I'll show you today, you can really use any of them, right? So we're looking for, the question is asking about CD and manganese. So let's quickly first find CD and manganese, and then we'll be able to answer our question. So the CD they were giving us is going to be, where is it? Sorry, I need to check the valency before I go too far. Of the CD and CD2 plus to CD, and not Mn2 plus to Mn. Okay, let's quickly go back. So we're looking for CD2 plus to CD. There it is there. I'm going to quickly highlight that so we've got it noted. There's CD2 plus to CD. And then we said M, and not Mn2 plus to Mn, right? Okay. So which one is going to reduce CD2 plus to CD, but not Mn2 plus to Mn? The options they gave us, before I look at our options, let's have a look at which one is going to then have that reduction happen. So remember, we need to find something that's going to have strong, right, reducing agents. Strong reducing agents are going to help us undergo reduction. So in this case there, what we need to find is we need to find something that's going to be stronger than where our CD is. So I'm looking from CD going up, because as I go up, my reducing ability increases. I find strong reducing agents there. So chromium, iron, Cr, zinc, that hydrogen with the hydroxide, chromium, manganese itself, everything going up is going to help me reduce the CD2 plus, right? But they said it mustn't reduce Mn, right, 2 plus. So if it mustn't reduce Mn2 plus, it means it can't be a stronger reducing agent than manganese itself, which means I'm going to be limited to this place and I need to look down here, right? I can't remember all of the other options, but I can definitely tell that zinc meets that criteria. On my diagram, it's a stronger reducing agent than the CD, but it's not stronger than the Mn, and that's what I need. So it must be good for CD, but it mustn't be effective for Mn. So zinc is there. All the other ones are probably going to exist in this space. They're probably going to exist probably up here, which means it's going to be up here where it's really just going to be strong enough to reduce Mn and CD, or they'll be down here, which means they're not even strong enough to reduce CD or Mn at all. But zinc, we can see, is in between the two of them. That's one that I can use to reduce the CD, but not the Mn2 plus. I hope that makes sense how we got to that answer. And that's how we use our table of standard reduction potentials, right? Don't panic. Again, if you didn't get that, we still have 2 more chances for you guys to score some points. But well done to everyone that got A. Give yourselves a round of applause. I'm super proud of you guys in that case there. Okay, the next one we're going to have is this question here, right? And this question says, the following hypothetical standard reduction potentials relate to a galvanic cell, right? So it's some kind of galvanic cell that's there. So we've got X2 plus an aqueous solution plus 2 electrons becomes X. The E cell value of that, or the E naught value of that, is going to become 10 volts, a positive 10 volts. Then we've got Y plus 1 electron becomes Y, and then the E naught value of that is negative 10 volts. Consider the following statements for this galvanic cell. Number 1, it says the EMF of this cell is 0.10 and negative 0.10 volts respectively. The EMF of this cell is 0.20 volts under standard conditions. Number 2, electrode Y is the anode. Number 3, X is oxidized. Those are your three statements. Which of the above statements are true for this galvanic cell? I'll give you guys 60 seconds to have a look and then answer the questions that follow. Okay. Quickly go for it. Read statement 1, statement 2, and statement 3, and then you must tell me in that case there which ones are going to be true out of 1, 2, and 3, and then select your answer A, B, C, or D. If you are new and you've just joined the session, what you need to do is simply post A, B, C, or D. Post the answer that you think is correct. Remember, it's important for us to all take part. It's important for us to all join. Please make sure you post in there. Wakile, thank you so much for your speedy response. You've given us the first answer for the day. Let's see who else is going to come through for us there on TikTok. Thank you, Kosa, for posting your answer. Thanks, Shudufato. Thanks, Sinki. Thanks, Tsetla. Thank you, Kensani. And thanks, Tapelo, for your speedy answers. We'll give everyone else 30 more seconds. If you've just joined us, welcome, welcome, welcome. We're doing some questions on electrochemical cells. Please just answer the question that's on screen. Thank you for everyone that has followed us. We're so close to our target. We said our target today is to hit 12,000 followers. We're at 11,984. So we're literally 16 away. So if you're watching on TikTok right now and you're not following us, please click that follow button. It's going to be much, much appreciated. And it'll give you access to really awesome content. Our page is full of really awesome videos that help you guys prepare for your exams. So we'll appreciate if you guys follow us in that case there. Thanks to Rufino for following us. Really appreciate that. And then you can share the live with your friends. Help them join. If you're finding this helpful, share it with your friends, and then they can join. They can also benefit from this session. All right. Okay. 10 more seconds for the answers. Guys, please post if you haven't posted your answers. We've got 10 more seconds. 5, 4. If you don't know, just guess. 3, 2, 1. Guys, golden rule, never leave a multiple choice question blank. If you don't know, at least guess. Okay, let's see what answers we got back. So TikTok, there's a couple of C's, B's, and maybe even some A's there. On Zoom, we've got a bunch of B's, 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 only B's. Okay, let's see which team is going to win this one. So the correct answer for this one, drum roll please, is going to be B, right? Let's have a look at the case. So we're going to look at 3 statements and then mark them correct or incorrect based on the facts. So we were told in this case there that the following are going to be the reduction the half reactions for a galvanic cell. So, right? So the EMF of the cell is going to be 0.20 volts, definitely, because a galvanic cell will always have a positive E0 value, right? And then in that case there, how do we work out that E0 value? Let's quickly go back to our notes. Working out the E0 value, we're going to say E cathode minus E anode. Cathode is where reduction happens, anode is where oxidation happens, right? So E cathode minus E anode is what's going to happen there. So we're going to basically then say the first one, 0.10 minus a minus 0.10. So this is going to be our cathode here, which is going to be the reduction, half reaction. And then our anode is going to be our oxidation, half reaction. So we know definitely that statement number 1 is going to be correct, right? Okay, number 2, electrode Y is the anode. Yes, it is. Oxidation happens at the anode. We already said that that's going to be our oxidation half reaction. That's going to be true over there. Then it says X is going to be oxidized. That's not true because the X is going to be our cathode. At the cathode, reduction is what happens. So X is not going to be oxidized, right? So X2 plus is going to be reduced. So this statement then will not be correct. So only statement 1 and 2 are correct, and that will give us the final answer that we wanted there, of B being the correct answer. Well done to everyone that got B. If you didn't get B, don't feel bad, guys. It's part of the learning process. The worst case scenario is you figured out what the right answer was, and hopefully you saw where you made your mistake. Okay, finally, we have one last question before we do the long questions, and then let's quickly give you guys a chance to have a look at that. So the last question is there. which one of the half reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride? Which of the half reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride? Okay, you have a choice of A, B, C, or D. I'll give you guys a minute to quickly look at it and pick which one you think is the right one, to see what happens there. So Kosa posts there, the hypothetical reactions were supposed to be given as reversible reactions. I didn't look at the question, but definitely in that case there, with our half reactions on our table, Kosa, they're usually given as half reactions. I took this from a previous past paper. They might have just made that mistake, but definitely it should have been given as reversible because they were both written in reduction format, but we know one of them is going to be oxidation. So then they should have been written as reversible. You're very correct, Kosa. Thank you for catching that one out there. Okay, we got some fast answers out there. Thank you so much to you guys for your fast answers on Zoom. Tapelo Puluso, Shurufato, Tsetla, Kaugelo, Rosina. Thank you guys so much for your answers. Thanks, Uteng there. TikTok gang, let's quickly put our answers in. Dinyoko, thank you for your answers there. Guys, if you've just joined on TikTok, remember, we've got a question up. This is the last multiple choice question. Then we're going to go into our long questions. Just post A, B, C, or D. Which one do you think is the correct one? Which of the half reactions below will be the main reaction at the anode during electrolysis of concentrated copper chloride? Thank you, Junior. Thank you, Kensani. Thank you, Lebohang there on TikTok for posting. Really appreciate it, guys. Thanks, Didi. Thanks, Prime. Thanks, Ditebuho. Okay, 10 more seconds. If you haven't posted an answer, guys, at least guess the one that you think might be the one, so that at least you don't leave the answer blank. Never, ever, 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 ever leave a multiple choice question blank. You've got a 25% chance of guessing it right. And if you don't put anything, you've got a 100% chance of getting it wrong. Okay, 5, 4, 3, 2, 1, and time is up. Thank you guys so much for putting the answers there on the screen. Let's quickly have a look at which one is the correct one. So which one of the half reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride, right? So let's look at copper chloride. In that case there, copper chloride is going to break down into Cu2 plus, chlorine, and then, sorry, chloride as well. Let me just use a different color for that. So then this is going to then become 2Cl minus, right? So we can see in this case here, copper is going to want to gain electrons, and then chlorine is going to want to lose 2 electrons. What do we call the gain of electrons and the losing of electrons? The gaining of electrons becomes what we call our reduction, right? Reduction is gain, oxidation is going to be loss. And what happens, which electrode has the reduction? Remember, red cat, so that's going to be our cathode, and oxidation happens at the anode, that's an ox, right? Anode there. It says which half reaction below will be the main reaction at the anode during the electrolysis of concentrated copper chloride. The anode is where oxidation happens. Oxidation is where we're going to find chlorine losing 2 electrons, like I've written there. Therefore, your final answer and the correct one is going to be D. If you got D, give yourselves a round of applause. Well done for that, guys. Just post a clapping emoji in the chat, and then I know that you guys did well. If you didn't get D, I hope you guys saw what the right answer was and how to get to the right answer. But basically looking at those particular steps there, and then we can see that these ones then will not be viable options for this question. Hope that makes sense. Hope it becomes a little bit easier. Let's jump into our long questions. We've got 35 minutes left in today's session. Thank you guys so much for everything that's been happening. You guys are really engaging like wonderfully in today's session. I like it. You guys are so interactive. It makes the lessons like this so worthwhile to do. Okay, let's jump into our long questions. Again, remember, Prime says I use the 4B table. Well done, Prime. Table 4B, table 4A, doesn't really matter, right? But if you use the one that you know that makes sense for you at the end of the day, that's going to be great. Cool. So question 8, start on a new page. 8.1, a piece of zinc is placed in a test tube containing an acidified permanganate solution. After some time, it's found that a redox reaction takes place. Use the table of standard reduction potentials to answer the following questions. Write down the name of the reducing agent, right? So we've got zinc and a piece, and then a permanganate solution that is there. Write down the name or formula of the reducing agent. So let's quickly go back and look at our table of standard reduction potentials. We're looking specifically at zinc and the permanganate ion. Let's quickly go down there. So I'll use 4B as the table that you guys mainly use. Let me just clear it from our last activities so we don't confuse ourselves with whatever's going to be there. So we're looking for zinc and permanganate. So I'm going to highlight those reactions there. So there's my zinc reaction there. And more particularly, what we have is zinc metal, right? So that's what we've got there. And then we need to look for our permanganate ion. And the permanganate ion, let's quickly try and see. This is the one part that I really suck at, is trying to find the specific one. So there's a permanganate ion down here. Let me just make sure I haven't lost or not seen any other one. And then for minus keep going up, I don't see any other permanganate ion. Yeah, I think that's the one that we need to look at there. So there's the reaction down there with our permanganate. If I missed it, guys, please give me a shout. We've got there, but what the species we're dealing with, what we're looking for there is going to be this here. And because it's in solution, we know we will have the water and we'll have that other H that happens in that space there. So that's what we're looking at in this case, right? Let's quickly go back to our question and see what exactly they need us to do, right? So in the question, this is what they asked us. They said, write down the name of the reducing agent, right? So the reducing agent is one that's going to undergo oxidation, right? So when I look at my table, there's two ways I look at it. It's going to be a spontaneous reaction. We know that. So I know the one with the more positive E naught value undergoes reduction. The one with the least positive E naught value undergoes oxidation. Or you can look at it as the one that's going to undergo oxidation is going to be the strongest reducing agent. The one that's going to undergo reduction is the strongest oxidizing agent. They wanted to know which one undergoes oxidation or is going to be the strongest reducing agent. Remember, strong reducing agents, right-hand side, we're going to go up. Strong oxidizing agent, left-hand side, we're going to go down. So in this case, I'm looking for the strong reducing agent, the thing that's going to undergo oxidation. That's going to clearly be zinc. On the right-hand side, I have to go up, up, up. Zinc is going to be the one that undergoes oxidation. It'll go from the right to the left, meaning zinc becomes zinc 2 plus 2 electrons. So let's quickly go back and answer the question there. And then the question says, again, the name or formula of the reducing agent. The reducing agent is going to be zinc, right? So you can write zinc, or you can simply just put Zn, right? Please don't put Zn2 plus, it's Zn, the metal, that is going to be the reducing agent to undergo oxidation, right? Thanks, Kansani and Prime, for your answers there. You guys are sharp and on the ball, okay? Guys, by the way, we are 10 followers away from reaching our target, right, of 12,000 followers. So if you're watching and you haven't followed us, please follow us right now. Share a link to a friend that you know is not following us so that we can get to 12,000 before the end of this live. But thank you so much for everyone that's been following us. 8.1.2, refer to the relative strengths of the oxidizing agents to explain why a redox reaction has taken place. So as I explained when we were looking at it, right, let's quickly go back and look at it. So the reason we're looking at this right now is we can see that zinc is going to be a stronger reducing agent. Remember that as we go up on the right-hand side, you've got increasing strengths of reducing agents. As I go down on the left-hand side, I've got increasing strength of oxidizing agents. So it's very, very important to note that now our manganese permanganate ion is a stronger oxidizing agent than zinc, right? And will oxidize the zinc to form zinc ions. Very, very important that our permanganate ion is a stronger oxidizing agent and is going to oxidize our zinc. So you can just write it in that exact same way there. Our MnO4 ion is a stronger oxidizing agent. Let me just erase this, sorry. And will oxidize our zinc. Okay, simple as that. Some very, very easy ways to score 3 marks in that case there. Then the next one, we need to look at question 8.2, right? So 8.2 says the standard, a standard electrochemical cell is set up as shown. So we can see there we've got 2 half cells, a nickel half cell and a manganese half cell. And then we've got something in the middle there, which is component Y. I want you guys to post in the chat, what is the name of component Y? You guys should all get this for these 3 marks. What is the name of component Y? And then we'll look at the function as well. Bonus points for giving me the function. Okay, thanks, Polisa, for that. So post me, what is the name and the function of component Y? I gave you guys 3 functions. Just give me any one of them. Thank you so much. You guys did really well. Y is a salt bridge. Now the question is, write down the function of component Y. Any one of the 3 functions will give me that. Well done, Letlhagonolo, for that very fast answer, is to complete the circuit, right? So any one of the following will work. Complete the circuit. Let me quickly write this. Complete the circuit will work. It will maintain electrical neutrality. And then also it keeps our electrolytes separate, but any of those 2 should definitely work. Well done, guys, for those 2 things. And the answers you guys are giving me, you guys are doing really, really awesome today. I appreciate it. You make this long weekend lesson much, much, much worth it. Okay. 8.2.2. In which direction will the electrons flow in the external circuit? Please get that part right. In the external circuit, what direction will the electrons flow? Choose nickel to manganese or manganese to nickel, right? Let's quickly go back. So what direction will the electrons flow? Nickel to manganese or manganese to nickel? I'll give you guys 2 minutes to quickly do that. Remember, you have to go refer to your table of your standard electrical potential to figure out what's going to really happen there. What's getting oxidized, what's getting reduced, and where do my electrons flow? Thanks, Kosa, for your fast answer there. Thanks, Lebohang, as well. Thanks, Kitumete and Rokotsu as well there for your guys' answers. Okay, let's quickly see. Okay, I'll give you guys 10 more seconds to post an answer. If you're not sure you were given 2 answers, you can guess, right? Thanks, Polisa, for your answer. Thanks, Dinyuko, for your answer. Okay, quickly get your answers in before I reveal what the actual answer is going to be. Thank you so much for the follow, guys. We're 6 followers away to reaching our target. 6 followers. I know we'll reach it. You guys are awesome like that. Okay. Thanks, Junior, and thanks, Didi, for your answers. Apologies. So the actual answer for 8.2.2, the direction is going to be from manganese to the nickel, right? It's going to be manganese to nickel. Let's have a look at why I say that, right? So let's quickly go back and look at our table of standard reduction potential. So we've got manganese and nickel 2+ and manganese 2+. So I'm going to just erase the stuff we were dealing with before. So there's our 1 reaction, which is our manganese half reaction. And then we need to find our nickel half reaction, which is going to be here. Okay, let me put these in here. So keeping in mind, right, guys, on the right-hand side, as I go up, I get strong reducing agents. On the left-hand side, as I go down, I get strong oxidizing agents, meaning the one as I go up, strong reducing agents are more likely to undergo oxidation, loss of electrons. So this is going to undergo oxidation. So manganese becomes manganese 2+. That's going to be the oxidation On the right-hand side, I mean, at the bottom there, I'm going to have my reduction half reaction, right? It's going to go in this direction there. So reduction, where nickel 2 plus 2 electrons becomes nickel. So what we're really going to see there is manganese is going to lose 2 electrons. Those 2 electrons are going to go all the way around, and they're going to join, sorry, not meant to be a W, it's meant to be an arrow. Those 2 electrons are going to go leave the manganese. Those could be the same 2 electrons that join the nickel 2 plus to become nickel, right? Those are my 2 electrons that move there. So from manganese to nickel is the direction that my electrons are going to flow. Let's quickly go back and mark it on our half cell. So we'll see here that manganese is on, it's going to get oxidized. So we're going to have manganese becoming manganese 2 plus in solution. Then I know that my electrons are going to then flow this way, that way, down. The electrons will then come back on this one here. And then what you'll find is your nickel 2 plus will come, pick up those 2 electrons, and then just become nickel metal on there, right? That's how this whole process flows. And then we've answered that question. Then it says calculate the initial EMF of the cell. That's quite easy. Remember what we said. We know the calculation for this is going to be E cell, right, equals the E naught for, you can write cathode minus anode, you can write reduction minus oxidation, up to you. Sorry, up to you. So reduction minus my E for oxidation, right? And then we said which one is reduction, which one is oxidation. Let's go put those, let's go look at those values on our table, right? That's why I said to you guys, remember, this table is so important. We're going to use it so much today. So we can see our reduction one is going to be, let me highlight it, at negative 0.27. And then our oxidation is going to be at negative 1.18, right? So negative 0.27 and negative 1.18. Let's quickly go back and plug those in. And then as we plug these values in, we can see the following. So reduction, we said, is a negative 0.27 minus, and then the oxidation was going to be a negative 1.18. Okay. Quickly pop that in your calculators and give me the answer that we get as a result. Welcome for anyone who's just joined us. Please, we're doing this electrochemical reaction. If you're not following us, please follow us right now. Thanks, Lucania, for following us. Thanks, Mathematica Series, for following us as well. Really appreciate it, guys. We are 4 followers away from reaching our target of 12,000 followers. So we really appreciate all the follows. Prime gave us the answer, really quick, really speedy there. So Prime, I want you to just double check that answer while you're still busy, right? So we have negative 0.27 minus a minus 1.18. Quickly double check it, but thank you for your speedy answer. You did really well there. Rokotwe then gave us an answer, which looks a lot more correct, and I appreciate that there. Tuki, also please go double check your answer. It's negative 0.27 minus a minus 1.08. So if you put it on your calculator, just like I've written it down, you should be fine, right? The brackets are important so that you don't make mistakes in your calculator. And then what you guys should see, the answer you should get, which Kensani gave us the right answer there as well as Rosie and Kitumetsi and Poloso, which is going to be 0.91 volts. Guys, please don't forget your units. Units are very important. If you don't put the units down, you end up losing marks. Okay. Awesome. That's a great one for us to do there. I hope you guys see how it is done. And if your answer wasn't correct the first time around, I hope you see where you might have made your mistake and how you do it better the next time, right? Okay, let's quickly go to 8.2.4. We've got 20 minutes left and I want to get through to my electrolytic cells questions as well. So 8.2.4, write down the balanced equation for the net cell reaction taking place. So remember, when we're looking at the net cell reaction, I showed you guys a little bit earlier that we take our oxidation reaction, take our reduction reaction, and then we put them all together, right? So if you guys can remember, let's quickly do that. So we start off with, let's say, our oxidation or reduction, doesn't really matter. Let me do the reduction reaction. So we know that we have nickel 2 plus 2 electrons, giving us nickel metal. Then the reduction, I'm going to leave my arrow in the same place. Right. Then the other one, I'm going to have manganese being oxidized, right, to become manganese 2+ plus 2 electrons. So I'm going to have my manganese there becoming manganese 2+ plus 2 electrons. Then I can put a nice line at the bottom of everything to ensure that I can then finalize this one. So we'll have a nice line there. And then first step I need to do is check if my electrons are balanced. So how do I check that? I've got 2 electrons here and 2 electrons there. So in this case, my electrons are balanced. I don't need to multiply any reaction. If they weren't, I would need to multiply them to ensure that my electrons would be balanced at the end. Once I'm done, I'm going to write down whatever's left over, making sure that I don't write my electrons down. I can then leave them out. So now on the left-hand side of my arrow, I'm going to have my nickel 2+, sorry, let me rewrite this manganese, giving us, we can see that we've got our nickel plus our manganese 2+. As simple as that, guys. Nothing too hectic, nothing too crazy. We are basically winning at this point. I hope it all makes sense. If you guys are still with me, please post a thumbs up emoji in the chat or on Zoom. Give me the thumbs up reaction so that I know you guys are with me. Thank you so much. They're coming through on Zoom. On TikTok, just give me a thumbs up emoji to know that you guys are with me. Thanks, Tato, there on Zoom. Thanks, Didi. Thanks, Dinyuko. Okay, fantastic. I can move on to the next question. Guys, we are 1 follower away from reaching our target. We are at 11,999. If you're still not following us, you have the special honor of being our 12,000th follower right now. So make sure you click that button quickly so you can become our 12,000th follower as I move on to our very next question. Cool. 8.2.5. It says the concentration of our nickel 2+ ions is now increased. Will the reading on the voltmeter increase, decrease, or remain the same? This is a question I want you guys to answer, right? So let's quickly go back. And they said our nickel 2+, so this here, the concentration is well done. That sound means we reached our target. So whoever that was, I can't see right now who did do the following, but whoever followed us now, you are officially our 12,000th follower. Thank you guys so much for helping us reach that target. So the question is asking, if I increase the concentration of our nickel 2+ ions, will the voltmeter reading increase, decrease, or remain the same? Okay, quickly give me what you think the answer is going to be. If I increase the concentration of my nickel 2+ ions, what will happen to my voltmeter reading? Increase, decrease, or remain the same? This is like multiple choice. If you're not sure, just take an educated guess, whatever you think feels right. Thanks, Kaukelo. Thanks, Kikmenzo, for your answers. Thanks, Kosa. And thank you very much for Nokumonga as well in that case. Cool. If you've just joined us, guys, we've got a question that says, here's a galvanic cell. If I increase the concentration of my nickel 2+ ions, what happens to the reading on my voltmeter? Does it increase, decrease, or remain the same? Thanks, Wakile, for that answer. Thanks, Bridget, for your answer. 10 more seconds, guys. If you're not sure, the worst you can do is to guess. Never leave a multiple choice question empty. If you leave it empty, you're guaranteed a 0. If you guess, you have a 25% chance of getting it right. Okay, 5, 4, 3, 2, and 1. So right, and I think Kosa gave it to us beautifully there. Think about chemical equilibrium, right? And think about rates of reaction. So in this case here, the voltmeter reading is an indication of our rate of reaction. So the more or the quicker my reactions happen, the quicker my electrons flow, right? The rate of flow of charge is current and your voltmeter, and the more electrons I have, the more potential I'm going to have as well. So if I increase the concentration, I'm going to increase the number of electrons going through, and I'll increase my voltmeter reading, which means the answer is going to then be increase for this particular question here. And the question didn't necessarily ask us for a reason, but I gave it anyway. But the final answer is going to be increase. And that is us done with galvanic cells. Don't leave just yet. We still have a question on electrolytic cells in our last 15 minutes. But thank you so much for those that have been posting answers. Give yourselves a round of applause if you got it correct. Even if you didn't get it correct, give yourself a round of applause because now you know what the correct answer is. You know what the right methodology is to follow, right? Okay. let's jump through. So we've got question 9. I'm going to take a short break, just 1 minute, in case anyone has got questions on the galvanic cell before I move on to the electrolytic cell. So I'll give you guys 30 seconds to get yourselves together. If you are happy and you don't need any questions, you want us to move on, give me a thumbs up emoji or just post happy, let's move on in the chat. Police is asking, why does it increase? So if we go back, what we can see, remember when you're dealing with rates of reaction, right? If you increase the concentration, I'm going to basically have my rate of reaction increase, meaning I'm going to have more electrons being put out there. And as I increase my number of electrons that are being put out, or electrons that are being taken up my nickel 2+ ions, I then basically will increase, because then I favor the reaction of my electrons flowing a lot faster. I'm going to have more electrons in circulation, meaning at that point, I'm going to then have a greater potential difference between my two half cells. So the voltmeter reading will increase in that case there. So I hope that makes sense. I don't see any further questions. I'm going to have a sip of water, and then we're going to jump straight into question 9 in our last 15 minutes. All right, let's jump straight into it. So question 9 looks as follows. Question 9 says, the diagram below represents a simplified cell used for the electrolysis of concentrated chromium chloride, right, CrCl3. Electrodes R and T are made of carbon, okay? Then they give us the diagram there. They show us what the diagram looks like in this case here. Then the first question, before the question, it says the net cell reaction is 2 chromium chloride becomes 2 chromium and 3 chlorines, right? Define the term electrolysis. So we did this one a little bit earlier on, and it's quite a simple one, right? That electrolysis is the use of electricity to produce a chemical change. It's that simple. I'll quickly just paste the answer so I don't have to waste time writing it. Give me 2 seconds to do that. Okay, there's our answer. Electrolysis is the use of chemical energy to produce chemical change. And this is one of those definitions where you can't get 1 mark. You either get 2 marks or you get nothing in this case, but it's an easy one. Guys, definitions are easy ways to get our marks at the same time. Let's jump at 9.2. It says the graph below, not drawn to scale, represents the changes of the mass of electrode T. Let's quickly go back and see that. So we have a battery, we've got chromium chloride, and it says electrode T is going to basically change in mass. How does the change look? It starts at 2.2 grams and it increases to a level of X after 10 hours. Write down the half reaction that takes place at electrode T. So let's quickly go back and look. So we know that we've got chromium chloride becoming chromium solid and chloride gas. So the only way a gas is not going to make an electrode gain mass, only the solid. So chromium must therefore be what's going to be happening there, right? Where chromium was probably going to be chromium ions then become chromium metal onto electrode T. So how do we do that? Let's quickly put down the half reaction. So we know that it's going to be chromium 3+. It's based on how it's bonded there with chlorine, because it's chromium Cl3. Cl is usually -1. So for 3 of them to bond with chromium, it's going to be chromium 3+, right? So then we can quickly go there and say, well, we're going to have chromium 3+. It's initially an aqueous solution, plus 3 electrons. It's going to pick up from the chlorines, and that becomes chromium in that case there. That's our half reaction that takes place at electrode T. And then we know that means whatever takes place at the other electrode is going to then basically be 3Cl-, right? Or just Cl- becomes Cl gas plus the electrons that come from them, and you can just balance it out. But I hope that makes sense for 9.2.1. Let's look at the following. A current of 2.5 amps passes through the cell for 10 hours. Calculate the total charge that flows through the cell in this time. Okay, so we've got current, they want charge. the formula that we need to use in that case then, we know Q is equal to I delta T, right? Let's do that. So we know charge Q is equal to I times delta T. We need to work out what that charge is, and then we're given the current. Simply, we can plug those values in. The current we're given is 2.5 amps, 2.5 amps. The delta T was given to us in hours. Remember, in SI units for science, time is going to be measured in seconds. So we got to then say 10 hours times 60 for minutes and times 60 again for seconds. And then when you look at that and you plug that into your calculator, it's a very simple calculation. You should get a final answer of 90,000 coulombs. So 90,000 coulombs, or if you wanted to, you can write it as 9 times 10 to the power of 4 coulombs. The units are very important. If you don't get the units, you're going to lose a mark, but then that's basically how you do that. Hope that makes sense to you guys there. Then it says the value of X as shown in the graph. We need to calculate the value of X. Let's quickly go back and see what they're talking about there, right? On the graph, we have the value of X. The value of X essentially is what's going to be the mass of electrode T after those 10 hours. How do we look at the mass of T? So we now know how much charge, right, has flown through the cell in this time. That charge tells us about the number of electrons that have gone through. We can then use the number of electrons and the half cell to figure out what really has been happening in that case there. So let's quickly use that and say, I'm going to use the charge to figure out how many electrons are going through and then how much of the metal has been moving through that particular case. So to do that, first of all, we know that electrode T is the chromium electrode. So I'm going to copy this half reaction because it's going to be very useful to us, right? Let me quickly move this up. So we know that half reaction, it was Cr3 plus 3 electrons to give us Cr. So what I was trying to say to you guys now, that we can look at it this way. We know that this much charge is going to be basically carried through by these electrons. So to figure out how much mass this Cr was gained at that electrode, I need to figure out how many electrons or how many moles of electrons were moved through by this charge. Once I figure out how many electrons, I'm going to use stoichiometry to find now how many moles of chromium were deposited on there. Once I know how many moles of chromium were deposited on there, I'm going to then basically take that and convert it into the mass in grams, and that'll give me X. Hope that makes sense. Let's quickly go figure that out, right? So the first thing I need to do is find my number of electrons, right? So let's call that a capital N. My number of electrons is going to be the total charge that we had above, the 90,000, divided by the charge of one electron, QE, right? So that we can basically do that. It was 90,000 coulombs overall. The charge of one electron is going to be 1.6 times 10 to the power of negative 19 coulombs, right? Plug that into your calculator and you should see that you will get an answer of 5.63 times 10 to the power of 23 electrons. That's how many individual electrons, right, that we are going to have there in that case. But we need to now figure out now how many chromium, what's this? Either electrons or the number of moles and the mass of chromium. So there's a number of ways we could basically do it, right? So once we've done that, we need to figure out now from that many electrons, how many of chromium are we going to then have? So I'm going to just use the number of electrons and say, we can clearly see for every 3 electrons, one chromium atom is deposited. So let me go find the number of chromium atoms simply by then saying, well, the number of chromium atoms is going to be the number of electrons divided by 3. That means I've got 5.63 times 10 to the power of 23 electrons divided by 3, right? When I divide that by 3, I end up with 1.88 times 10 to the 23. That's now the number of chromium atoms that I've got there. Number of atoms is great, but the question is asking us to find the mass that we're dealing with. But that's okay. We've got stoichiometry. We can definitely figure that out, right? So using stoichiometry, I've got the number. I need to go find the moles. Once I've got the moles, I then go find the mass in grams. So let's go find the number of moles. Given the number, that equation is going to be N is equal to number divided by Avogadro's number, right? In that case there, we can say, well, the number we're given is 1,88 times 10 to the 23 divided by 6,02 times 10 to the 23. That's Avogadro's number. It's a number that we should all know very well. Plug that into our calculators, and then you see that you should get an answer that looks like the following, which is going to be 0,31 moles. That's my number of moles. I still haven't answered my question because the question is asking for the mass, right, of that electrode. So the mass gained by that electrode there, we're going to take the number of moles and work out now the mass. So remember, how do we do that? N is equal to small m over big M. We're looking for the mass in grams, so we can substitute and then solve, right? So the number of moles we're given, 0,31, is equal to my mass in grams, which I'm trying to solve, divided by the relative molecular mass, right? What's the relative molecular mass of chromium? You can quickly go to our formula sheet and find that value there. So there's chromium with a relative molecular mass of 52, right? 52 is a value that I need to go plug in there. So let's go back and substitute it. So then I've got, zoom out. That's divided by 52. So 52 times 0,31 in your calculator, you will plug that in and you should find, you get an answer of 16,12 grams. So that's the mass now of chromium that I've got there, right? But remember one thing that's important. They gave us this table, right? And then they said the mass of the electrode there is going to be X. We started with the mass of the electrode being 2.2, and then it worked its way up to X. And then they told us in that time there that we had a current that passes through for 10 hours. And then we worked out the total charge that flows through. That charge helped us work out how many electrons and how much was deposited. So now that's what was deposited through there, and that's the mass that we basically then develop at the electrode at that point. I hope that makes sense. So that's what was deposited. Now they want the full mass X, because what we just calculated, don't forget, we didn't calculate the full mass. We just calculated this change here, right? Oh, that's not a great curly bracket. We just calculated this change here. That is the answer that we got if I call it Y. We need to find the full mass of the electrode. And the full mass is going to be our answer plus this 2.2 grams. And that's very simple to do as a final step. So therefore, the mass total is going to be our answer, 16.12, plus the original 2.2 grams, which will give us a final answer of 18.32 grams. And we are done with this question, right? Thank you so much. Haukelo, you gave us the answer there. You were working really well and keeping up to pace with us. I really appreciate that, guys. That brings us to the end of our lesson for today, guys, with electrochemistry. Hope that makes sense. I hope it really made sense. I hope for those that had done this topic at school, it makes more sense now. And those that hadn't done the topic, it might still be a little bit shaky, but don't you worry. When you get to school, it'll make a lot more sense. Then come back and watch the lesson. If you guys are happy and you feel like we've helped you in the session, please give us a thumbs up or a clap emoji. If you have any questions, this is the time to ask. And if there's no questions, we're going to end the day, and you guys must have an awesome rest of your guys' weekend. Okay. Polo, so thank you so much to you too for attending. I'll definitely see you guys on Monday. Remember, next week, guys, we're starting with our revision sessions. So what we're going to be doing next week with our revision sessions, we're going to be doing paper 1. So we have our lives. For those on TikTok that don't know, our lives are Mondays to Thursdays. So Monday and Wednesday is maths. Tuesday, Thursday is physical science. So next week, we're going to be doing paper 1, right? Godfrey, please don't annotate the screen. It's very distracting for everyone who's trying to watch, especially for me as the presenter, because now I have to stop to go erase what you're writing. So next week, we're doing paper 1. So we're going to do the first half of paper 1 on Monday. Second half paper 1 maths on Wednesday, and then we're going to do physics on Tuesday and Thursday, covering half of the questions of paper 1, half of the questions of paper 2. Jessica's asking, they're on TikTok, what time? Our lives are going to be 6 p.m. to 8 p.m. Monday to Thursday. And in the next 2 weeks, we're now doing revision. So we won't be doing the theory, like we start the session with the theory. If you want to catch the theory, go back to our YouTube and watch the recording. So we've been recording every session. Next week, we're just doing the past paper questions, and it's time for you guys to really come in and ask questions. And let's really do application, so that you guys know how to apply these problems and then come with lots and lots of questions. Kaukela says, thank you so much. See you next week. Thank you very much, Kaukela, for joining. I know it's a long weekend and people want to rest and sleep, but you guys made sure you put your futures first. That's why you guys are going to excel, and we really appreciate it. Thank you guys so much. I'll see you guys all next week. It was a really awesome time. I'll hang around to see if there's any more questions, and if there's nothing else, if there's no other questions, you guys can sign off, and I appreciate your time. Thanks, guys. Have a great weekend. Cheers. Guys, remember, if you haven't followed us, please go follow us on TikTok, on Instagram, on YouTube at The Learning Space ZA. Thank you for all the followers, guys. You helped us reach our target, and it's really awesome. Let's get into the weekend with our favorite tune, guys. Thanks so much. If you guys want us to change the songs, please let us know. We like the song. If you want us to use different songs every time for starting and ending, let us know, and maybe you can post there. Go to the live recordings and comment there which song you guys want us to use for the other ones. But I'll see you guys next week. Cheers.